Okay, so now we will go through one more example pertaining to t-test. Okay, so if you look at this question's parameters, now Sn is unknown. I mean sigma is unknown. Okay, so when this is provided, you know automatically t-test is coming your way. Okay, so before you calculate your t-test, you execute your t-test, you must always calculate your Sn minus 1 or your Sx, so to speak in the GC's vocabulary. So remember your Sn minus Sx, which is equal to Sn minus 1, is actually equal to square root of n over n minus 1 times Sn, okay? Which is equals to, in this case, 210 divided by 99 to the power of 0.5 times what? 2000. So we are looking at 2010.08. Okay, this is the unbiased estimate of population standard deviation. Remember, we can never say this is equal to sigma. We are only saying this is the unbiased estimate only. We will never know what is the actual value of sigma. So this is a right tail t-test. Okay, so just use someone help me use the GC to get the p-value first.
0.97.
Say that again. Wait.
No. Wait, why is yours 0.9?
Hang on.
This is the t-test.
I got 0.0246.
What?
Okay.
Yeah, 0.0246.
Okay, t-test, right? T-test, okay. Then your Sx is this,
Yeah.
Okay. Okay. Sam, you got the value now?
Hang on.
I think your GDC is broken.
Wait. Oh, okay. I keep on doing the wrong tail test.
Okay. Okay, Edward, you got this also?
Yeah.
Okay. So this one, your p-value is less than your alpha, so we will reject. Okay. Reject means reject H naught. Okay. So this is a t-test, so there's no point. Okay, so if you want to, you can talk about your X bar curve first. Okay. Everything will hinge upon the X-axis. The Sn is irrelevant right now. If I were to talk about my X bar curve, X bar is actually a t distribution with 5,400. Then 2010 square over n. Okay, t curve. Also I forgot. Degrees of freedom is actually 99. Okay, n minus 1. Okay, so this is the t curve. Unfortunately, if you were to use so if I were to sketch out the t curve like this is 5,400, of course. And this is a right tail test. So you will have a critical value here. Then this area here to the right side is 0.1. Okay. But I think if you were to use the inverse t expression, right, then the inverse t doesn't allow you to enter these things at all. Can you all try? If you press the inverse t, they only ask you for your sample size and your area only. The INVT function in the GC. Okay. Statistics, then distributions.
Area and degrees of
Ask you for
freedom.
area and degrees of freedom.
Yeah, so that will be inverse t 0.9, then degrees of freedom is 99. Okay, this will give you
1.29.
1.29. Okay, everybody got this?
Yep.
Okay, this 1.29, right, is actually the normalized critical value. Okay, so you can see that the T curve is a lot less built in compared to the Z curve in the GC's context. The GC, if you want to operate on the Z curve, right, we can do inverse norm, a lot of flexibility in the sigma and the mu. Okay, like what you see in the blue curve here. But if you're operating on the T curve, right, the GC only recognizes one T curve only. There is the basic T curve, the one with the center 0. Because the GC has got too many things to handle for pertaining to the T curve already. Because it needs to handle the degrees of freedom, which is a very bothersome thing, computational wise. Okay, so the GC only recognizes one basic T curve shape, the one with the center 0, which is the normalized T curve. So how do I link this 1.29 to the original black curve, the convex bell curve, right? Is this 1.29? So 1.29, right, is actually equals to CV in the context of the black curve minus 5,400, then divided by sigma over square root n, which is 2010 divided by square root of 100. Can you understand what's going on here? Then from here you can calculate your CV if you want to. Understand what's going on, guys? Okay.
Yeah.
So I'm trying to reverse engineer the values. Then you should get some stuff here. Okay, if you need to.
Wait, sir. Sir.
Yeah.
You're saying that for the T curve, is it you cannot calculate the critical value via GC?
Yeah, you need to go through the normalization process by yourself, by hand.
So only the Z curve that can be done by
Yes.
GC.
Yeah, you can see that when you do the inverse norm, the GC actually gives you the flexibility of entering your mu and sigma, right?
Yeah.
Yeah, but the GC, but the the inverse T doesn't give you this function at all. Understand?
I see. Okay.
Yeah, so you need to be aware of the limitation of the GC so that when a question comes, you will know what are the approaches. Don't get limited by your technology. Okay. So this is when I use the inverse T to get it out. I can also choose to do an inverse normalization of my 5,400 right away if I want to. Okay, so this here, once you must always establish a 1.29, of course. Okay, this is for sure that you must do. Okay, here what I did over here is I unnormalized my 1.29 to see where will 1.29 fit in the contextual curve, which is the curve center at 5,400. Alternatively, I could have tried to normalize my 5,400. Gee, it's not center, it's not 5,400. Sorry for this. Should be 5,000. Made a mistake here. Sample mean is 5,000. Oops. This is 5,000. 5,000. 5,000. Okay. So this is one method. From the basic curve, I went back to the convex curve. Otherwise, what I did was after you establish the 1.29, right? What you will do is you will normalize your sample mean of 5,400. So your normalized T, so we'll use T, which is our test statistic. Is equals to 5,400 minus 5,000 over 2010 over square root of 100. Okay, we will always be using 2010 because 2010 is the unbiased estimate of sigma. Okay, so if you go through this, you will get 400 divided by
It's 1.99.
4.99.
1.99.
1.99. Okay, good. So this is equals to 1.99. Okay, so if you compare, it's obvious that 1.99 is greater than 1.29, right? So we reject H0 also. Because remember, 1.29 is actually your goalpost because we inverse T 0.9. Okay, 1.99 is based, 1.99 here is based on your sample mean. Okay, your normalized sample mean, which is aka your test statistic. Understand? So there are many ways of going about this. If you want to calculate your critical value here, right, based on my option 1 that I created here, I'm sure your option 1 will also be less than 5,400, okay? Because you're operating beyond the goalpost, hence we reject H0. Everybody can follow this?
Yes.
Let me just evaluate this.
Yeah.
29 and plus 5,000, okay? This one, we actually got 5259. 5259. So actually your goalpost is 5259. So we are actually operating in the black region. So we obviously reject H0. So you can see that It's the same logic as your Z, just that in the world of the T curve, we do not have the luxury of be flexible in our mu and sigma. Okay, that is the biggest issue. Okay, but otherwise, in terms of getting your conclusion from your H0, H1 or whatsoever, right, it's all about these things only. Okay, everybody okay with this? Ken?
Yeah.
Yes.
Okay, so just remember you have these three angles of looking to get a conclusion. In terms of your technology, you can enter the raw data values or you can have your summary statistics. For summary statistics, when it comes to t-test, they are bound to want to test you on this thing first, okay? If you cannot even get this, then obviously die, okay? So remember, this thing is not sigma, it's the unbiased estimate of sigma. We are not saying that it is equal to sigma exactly, we are just saying that it's a good enough replacement for sigma in the context of the question or any sampling technique that we are doing, okay? Okay, with this, you need to move on to the other aspects of hypothesis testing, namely what are the weaknesses or the blind spots of this. So there are two kinds of errors in general. So if you look at this picture that I have for you, in actual fact, if H0 is true, then you go and reject, you will make a type 1 error. If H0 is actually true, but you feel, if H alpha means H1 is actually false, if H0 is false, then you fail to reject. It's like this. Okay, this one should not matter. Okay, so in simpler English, it's like this. Okay, I always remember it this way. Okay, so false positive. So to create so when you choose, when your conclusion is to reject H0, right, there is a possibility that you have made a type 1 error. That's all. Okay, so the probability of a type 1 error, and your syllabus requires you to know how to calculate the odds of both type 1 or type 2 error depending on the situation. So the odds of a type 1 error is easy. It is simply alpha, the goalpost that you created for yourself. Okay, why like that, right? It's just because if you set your goalpost to be 5%, 0.05, that means that anything whose event is less than 0.05, you choose to reject your hypothesis, your null hypothesis already. Okay, you choose to not accept such things can happen to you in the real world. But truth is, there is really the odds of such an event really happening, right, is not zero. So it's actually plausible that this thing can happen, but just that you never believe that it will happen to you, such like a lucky draw like that. So you really unluckily or luckily obtain such a rare sample, then it forces you to wrongly reject H0 as a result because you don't believe that you can obtain such a rare sample. Okay, so the argument is really simple. It's just like this. Okay, understand? So for example, if you are a casino regulator, again, whenever someone strikes jackpot 3 times in a row, you choose to declare that that guy is a fraud immediately. But maybe that guy today really happens to be the luckiest guy in the whole universe. Then he struck jackpot 3 times in a row. There really is such a probability. It's a non-zero number, but you just don't believe. Hence, you arrest him. That's all. Okay, wrongly. Okay on this?
Yes.
Okay. Everybody okay? Type 1 error is easy. Just say, when the question say find the probability of type 1 error, just say it's alpha. That's all. Okay. It is type 2 error that will be the problem. Okay. Type 2 error, when you want to do this, always go through this. Okay. Write down the definition. False negative, fail to reject when you should. That means your X bar is not inside the critical region. Okay, because you failed to reject, you did not reject H0. Okay, so to calculate type 1, when you should means the original hypothesized value is wrong. So to do this, the question is to give you the real population mean. Okay. Okay, this one is an error here. Don't worry about this first. Okay, sorry about this. Okay, what do I mean by that? Let me just go through with a numerical example. Okay. Okay, this is the meaning of a type 2 error. Okay, this one is not in critical region. Okay, so if you look at these values first, Okay, this is a z-test. Can someone give me the p-value first?
Um, 0.9997.
Eh?
Huh?
0.99.
9997.
Okay, what if I
Wait.
turn it to a left tail test?
Okay. Uh, 0.000233. I
Oof.
feel like we did that before.
No. 0. Okay. 0.000243.
233.
Okay.
We actually did that.
Yeah, okay. Failure. Okay, sorry, let me just change things a little bit. So this one, we do it to, okay, I think this one is 5, okay, change this to 5,300, change the X bar to 5,300.
Is it still right tail test or left tail test?
Right tail test.
Zero point zero six six eight.
0.0668.
Yeah.
Okay. So p-value, okay, it's based on this. Your p-value is equal to 0.0668. Okay, so obviously we do not reject. Okay, so when your conclusion is do not reject, right? You obviously are not in danger of making a type 1 error, but you'll be in danger of making a type 2 error. Okay, because to make a type 2 error means you fail to reject when you should be rejecting by definition. Okay, when your conclusion is to reject, then it's impossible that you will make a type 2 error. You will only be making a type 1 error at most. Everybody can follow now?
Yes.
Okay. Okay, so now the issue of type 2 error is the hypothesized mu here, right? 5,000 is actually wrong. The actual mu is actually 4,500. Okay, this is impossible. Let me just change this, make it more plausible a little bit. Okay, so if you focus on the rate side of things, right, what happens was you had a hypothesized curve, 5,000. For some issue here, you will have, okay, let's calculate the critical value first. So the critical value is equals to inverse norm 0.99, 5,000, then sigma over square root n. Okay, can someone give this first?
Four six five.
465, that can be right.
5465.
5465. Okay. So this is our goalpost. Okay. This area here is worth 0.01. Okay, everybody can follow on. This is what we have been doing in the first hour. Okay. So the rule of rejection is do not reject if your X bar is less than 5465, right? So don't reject if X bar, your sample mean, is less than 5465. Agree? And this is the rule that may cause us to create type 2 error. Understand? So understand so far? Because to make type 2 error means you must not reject in the first place. So now the question actually adds up by telling you, hey, your mu was actually wrong. The actual mu is actually 4,800. So the bell curve is not centered at 5,000. The actual curve is actually centered at 4,800. Okay, so this blue curve here is the hypothesized. Correct? Because you hypothesize it at 5,000. But then now the question will have to tell you this real mu. So the real mu is actually 4,800. So the real bell curve is actually like this, slightly to the left by 200. So this is the real curve. Okay, everybody can understand what's going on so far?
Yeah.
But the goalpost of 5465 still stays, right? Because the goalpost is created based on your alpha and your sigma and the settings of the test. So the actual type 2 error, right, is the area to the right of 5465 under the red curve. Okay, that drawing. So the type 2 error is actually here. The area to the right of 5465 under the real curve. So type 2, this is type 2 error. Area of critical region under the real curve. Okay, so if you come back to the definition that we have over here, right? So it's actually like this. So how to calculate the probability of a type 2 error, right? Is probability type 2 is equal to probability X bar is less than 5465, because that's the rule of non-rejection, given that mu is indeed 4,800. Okay, so I always write this down for myself. So you must first calculate your benchmark first, the benchmark for rejection or non-rejection. Then you must also know your actual mu values, which will be provided by the question. Okay, so now this becomes the sigma still stays the same. The sigma is the same, only the mu has changed. So here, this is norm CDF negative infinity to, well, what's wrong with the stylus? Negative infinity 5465. The actual mu is 4,800, and then the sigma is 2,000 over square root n. So it's 2,000 over square root 100, like this. Understand? The type 2 error is usually quite a decent value. It won't be like alpha so little.
It's 0.9995.
0.9995. Okay, so be it, because I give these values in a very extreme sense. Okay, understand? Because it's BS in the sense that because I'm doing a right tail test, but my actual mu is on the left side of the hypothesized value. Okay, but can you understand the logic behind this? Okay, let me run through with you what it means again. So type 2 error is you fail to reject when you should. Okay, so if you look at the original settings of the question, your hypothesizing is 5,000, then with the following parameters in the red box. Then we first started by saying that a p-value is 0.0668. So we do not reject because it's higher than 0.01, the 1% value. So if you view it on the X bar curve, the blue curve, the center of the curve is 5,000. Based on the alpha of 0.01, we can actually calculate the goalpost. The goalpost is 5465 by doing inverse norm 0.99, 5,000, then with the following parameters, which is something that you should be well versed in by doing the past few examples already. Okay, and it's equal to 5465. So by right, what this 5465 is trying to tell you is this: we do not reject whenever your X bar is less than 5465, or you will reject whenever your X bar is greater than 5465, the opposite statement. Okay, and it's coherent with what we have. Since your X bar is indeed 5,300, we are not operating in the critical region, hence we do not reject. But that's usually the first half of a type 2 error question. The second half of the question is to calculate the probability of a type 2, given that mu is indeed 4,800 over here. Okay, so to do this is actually a conditional probability question. But to see this graphically, it means that if I sketch out the real curve, assuming that sigma is still the same, the real curve is centered at 4,800 with the same shape. But the goalpost, which has been implanted by you, by the parameters of the question, right, will never change. So the goalpost is still here, 5465. But now the type 2 error, right, is actually just the red portion. We are operating under the real curve. Because when you went to do your sample, right, the sampling actually came from the red curve, not the blue curve. Understand? You all get what I'm saying? The real Singaporeans' income is actually based on the red curve, not the blue curve. We believe it's the blue curve, but it's actually the red curve. So when you actually going to obtain your sample of Singaporeans, right, you are actually drawing from the red curve. Okay, so when it comes to calculating the actual probability, we must be basing it on the red curve then. Okay, this is the meaning of type 2 error. This will be considered this one and PGF, right, are considered the hardest components pertaining to paper 3 because it's a 1 hour paper and it's time consuming. But it's also the kind of question, right, that will distinguish the A students from the rest in general. Okay, everybody can follow this. Okay, so I'm giving you the very simple example because it's a Z test. If this was a T test, then things get more convoluted in the sense that there's an extra step in terms of needing to operate on the basic plain vanilla, the -3 to 3 T curve. Because the T curve doesn't allow us to do this kind of normalization so easily like this over here. Okay, there will be an extra step, that's all, if it's a T distribution. Okay, but the logic wise, I'm just giving you all these simple examples first because I want you all to get used to the logic behind this first.
Okay.
Okay, Matthew, has our teacher taught type 2 error also already?
You just started teaching yesterday, so no.
Oh, okay.
Not really touched on that.
Okay, so this is always the time that, depending on how fast or slow your class progress along the main parts of hypothesis testing, right, it will determine how much time your teacher will spend on type 2 error in general. Okay, if you don't feel comfortable with this type 2 error, don't worry, I don't expect you to master this today. But type 1 error and then the various maneuver pertaining to a Z test or a T test, 1 tail or 2 tail, are stuff that you must know very, very well first. Okay? At least for today, you must make sure your maneuver is okay. Okay? Because last week I spent the time going through the various vocabulary and the logic behind hypothesis testing only. Okay? So today is about actually knowing the various angles to get your conclusion and stuff. Okay? Any questions on this first? Anybody? Anyone? Yes, no, yes?
Oh.
Okay, otherwise, let's hang up first. You all can go take a couple of minutes break, then I'll send you all the link again. Okay, this is the last one already, at least for today. Okay, Ken?
Okay.